The diagram you see up on the board is known as a curved lens. There's two names that we associate with this curved lens. Anybody remember what one of those names is? Yep. Converging. Yeah, it's a converging lens. All rays that are parallel to the principal axis, and that principal axis, by the way, is this line right here, right? All rays parallel will converge at the focal point. That's why we call it a converging lens. What's the other name for it? Converging or, yep, right, converging or convex. Thicker in the middle than it is at the edges. Rays converge at the focal point. That is, rays parallel to the principal axis converge at the focal point. We got all kinds of things on this that we got to be aware of. We say that this line is the principal axis. This is my focal point. We would say that this is 2F, but really that's just a spacer. Same over here. This is F, but it's not really the focal point. It's just a spacer, the same distance away from the lens that the focal point is. This is 2F, same deal. This is our object. And our object could be anything, right? It could be the newspaper that you're trying to read through the magnifying glass. It could be the car that you're looking at upside down out on the street when you're projecting the image through a lens. It could be the condos across the street if you're trying to project that image. With the demonstration we did here last week, could be the Canada flag that we had up on the board. The object could be anything. We're just representing it by an arrow. Now, if we want to find the image of this, what it looks like through the lens, then, well, we could look at any one of a number of rays. In fact, we could look at millions of different rays of light that are reflecting off of this object. But we're going to pick two. And the reason we're going to pick those two is because they're convenient. They're convenient and they're predictable. There's millions of rays that we could analyze and that we could, through sometimes a complicated analysis, determine where they go. But if we know exactly where these two particular rays go, why wouldn't we just pick those, since that's all we really need? First ray goes from the top of the object where? Maddie, where does that first ray go from the top of the object where? There? Oh, right there? There? There you go. Yeah, I know, you got it. Parallel to the principal axis. And the reason we make that one parallel to the principal axis is because we know exactly where it's going to go. It's very predictable where it's going to go, right? Taylor, where's that going to go? Good. It's going to go down through the focal point. Good. Now, that second ray, Quinn, where's that second ray going to go?
Goes to the optical center.
Good. That optical center right here. Okay, where does it go after it goes to the optical center, Quinn?
At the next point where they intersect.
Yeah, okay, so it goes straight through, right? Straight through the optical center right there. We find that they intersect over here. If they started at the top of the object, then they're going to end at the top of the image. And of course, we always draw it, whether it's the object or the image, from the principal axis. So down from the principal axis, intersecting there. What do we say about this image? The three characteristics or attributes of this image. What's one of them? It's inverted, yeah. It's upside down. It is, Blake? Smaller, yes. And it is, Logan? It's real. Real meaning that we could, if we wanted to. Yes. Where could we see it? We could project it onto a screen, and we know that we could project it onto a screen. We know that it's a real image because it's solid lines that intersect. All right, let's do one more of those ones. Let's do, this time our object is really close to the lens, inside the focal length of the lens. First ray, parallel down through the focal point. Second ray is going to go down through the optical center, keeps going straight down. They don't intersect on the right-hand side, so what are we going to do with these? What are we going to do with these, Laura? So we extend them back, right? And find out that they intersect back here and behind the image. So, Maddie, what's one of the characteristics of the attributes of this image? Good, it's bigger, okay. What's another one? It's bigger and it's virtual. Yeah, okay, it's virtual. How do you know that it's virtual, Blake? Right, it's dotted lines intersect, which means we could not project it onto a screen. If we want to see this, we have to physically look through the lens to see it. Finally, it's bigger, it's virtual, and it's upright, right side up, right? This is the magnifying glass, right? Okay, let's take a look at just one of these, because when you drew the ray diagrams for these last week, actually we'll do a couple of them just to demonstrate that they are the same, but You know that when you do the ray diagrams for these last week, the ray diagrams ended up all being, giving you the same characteristics. The image might have been varied in size a little bit, but it was always smaller than the object. And it might have varied in position a little bit, but it was always virtual and so on. Okay, so we draw our first ray, parallel to the principal axis. By the way, what kind of lens is this? Two names for it. What's one of them? Concave, caved in the middle, or, diverging, right? Which means that rays parallel to the principal axis diverge away from one another as opposed to converge. All right, so here's our first ray, parallel to the principal axis. Where does it go from there? Down here? Down here? It's going to diverge up here. If we took a ruler and just placed it at this point and at this point, then we could draw our line. Dotted on the left side and solid on the right side. So we've got our extension back through the virtual focal point. And then we say we got our next ray that goes down through the optical center as it always does. They're going to intersect right here. What kind of image do we have? It's virtual image. Yeah, it's a virtual image. Really, it's two dotted lines that intersect, the extension of the refracted ray, but you don't really have to draw the second one, dotted line. In the end, we know that dotted lines are intersecting here, so it's virtual, it's upright, and it's smaller. And no matter where you draw that object, let's draw it really close now. No matter where you draw that object, you will get the same three characteristics. First ray will say parallel up away from the focal point. Let's extend it back. Second ray is going to go down parallel to down through the optical center right here. Okay, where they intersect right here. If we look at the last diagram we drew, we can see that the image has gotten bigger than it was before, but we can still see that it has the same characteristics. It is still smaller than the object, even though it's bigger than it was. It's smaller than the object. We can tell that it's upright, and we can tell that it's real or virtual. Virtual. Whenever you draw a concave lens or diverging lens, you're always going to get a virtual image. There's some patterns that are starting to form here. Okay, some people, to be honest, some people will remember those patterns as opposed to choosing to draw ray diagrams. You're never on a test going to have to draw a ray diagram. We draw ray diagrams so that we can get characteristics. But some people are going to start recognizing patterns. Like for instance, if you have a diverging lens, it will always be the same characteristics. Virtual, okay, upright, smaller. If you have a virtual image, it will always be upright. Okay? Not always smaller, sometimes it's bigger, right? In the last type of the convex lens, it was a bigger virtual image, okay? But it will always be upright, virtual. They always go together, okay? If you have a real image, it's always inverted. It's always upside down. Sometimes smaller, sometimes bigger, but it's always inverted. And if you go through the order of the ray diagrams we drew, right from the very beginning, we started off, remember, real, 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 then we had no image, and then it became virtual, and then it was virtual for the next 5, right? So it becomes real, 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 none, virtual, 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 and so on. 6 virtuals. Make sense? So remember those patterns? Great. Okay, draw the ray diagrams every single time? Great. Whatever it is that works best for you and your mind, the way that you think. Okay, let's take a look at a little bit of math here. I gave you these equations on Friday, but we'll go through them again here. First equation that describes curved lenses is our thin lens equation. It says 1 over f is equal to 1 over do plus 1 over di. F is the distance from the focal point to the lens. Do is the distance of the object to the lens. di is the distance from the image to the lens. We had our magnification equation as well, m. M just stands for how big the image is compared to the object, the magnification. If it's 17, it means our image is 17 times bigger than the object. If it's 0.5, then it means our image is half the size of our object. The magnification is hi over ho. That's the height of the image compared to the height of the object. But it's also equal to negative di over do, which is the negative of the image distance divided by the object distance. It's important to have that negative in there to maintain our sign convention, which we'll look at here again right now. Remember the first three variables that go together, f, do, and di, we'll color those blue. And then our next equation, our variables that go together, ho and hi, we'll color those green because kind of a pattern with the sign conventions for each of those colors. F is positive when? What's the word that goes with blue here? Okay, what's the word that goes with blue to describe positive or negative? That first equation, the lens equation, 1 over f is equal to 1 over do plus 1 over di. All the variables in that equation are positive if they are good, if they're real. So a real focal point, it's positive. A real object, it's positive. A real image, it's positive. Make sense? All right, when do we have a real focal point? If it's a converging lens. When do we have a real object? Well, for us in Physics 30, it's always. Okay, that's not always necessarily going to be the case in your physics career. If you take physics in university, you may see a system of lenses. Here's a lens, here's a lens. Light goes through the first lens, forms an image, and that image becomes the object for the second lens. That object can sometimes be a virtual object, but we're not going to see that in Physics 30. So for us, it's always a real object, positive do. And the image, well, it's real. Remember in the first three scenarios, with convex lenses, the first three scenarios, we got a real object, sorry, a real image, and then we had no image, and then for all the other ones, we had a virtual image. So you can imagine, we filled this in on Thursday. F is negative if it's virtual focal point, and that happens if it's a diverging lens. It's never, do is never negative for us. Di is negative if it's a virtual image, and it's a virtual image in the last 6 ray diagrams. Okay. What about HO? HO and HI are based on not real or virtual, but upright or inverted, right? HO is positive if you have an upright object. And HI is negative, HI is positive, sorry, if you have an upright image. Now, there is a connection here, because you guys remember the characteristics, sorry, the trends, right? You guys remember the patterns of this, of the real and virtual and so on. If it's a real image, it will always be upside down. If it's a virtual image, it will always be right side up. So you could say that HO is, HO is almost always going to be positive, but HI, you could say is positive if it's a virtual image and negative if it's a real image, because it's always going to be upright if it's virtual and upside down if it's virtual. The reason that I've written it this way is to keep the pattern between HO and HI. And also, I don't want you to get mixed up here, right? Up here, if it's real, it's positive. HI is positive if it's a virtual image, because virtual means upright. So my suggestion would be, even though there are those patterns, my suggestion would be, remember the signs this way. Okay, keeping HI and HO together, and keeping F, DO, and DI together. Finally, M. M is positive. It kind of doesn't fit into either one. It's positive if the object and the image are on the same side of the principal axis. So in other words, if they're both upright or both inverted. So you get a magnification of +7, means the image is 7 times bigger than the object, and they're both upright or inverted. If you get an image that's negative, or magnification that's -7, then the image is 7 times bigger than the object, but it's flipped over. And if it's flipped over, you know it's got to be a real image, if you remember those patterns, right? So that would tell you that it's flipped over and real and bigger. If you get a magnification that's plus 0.5, the image is half the size of the object. If you get a magnification that's, and you know that it would also be a virtual image, because you get a virtual image upright. If it's negative 0.5, you get a real image, you get an inverted image, it's flipped over, and you know since it's flipped over that it has to be real, because that's when we get real images, is when they're inverted. If you remember those patterns. Okay, finally, we did an example, but we kind of rushed through this towards the end, so we'll go through this again, still fairly quickly, but for a second time, so that you're maybe feeling a little bit better about it. It says a 2.5 centimeter high object is placed 10 centimeters from a diverging lens. The first thing I want to do is circle this, reminding me that my focal point here is negative. Diverging, whenever you see diverging, f is going to be a negative value. Determine the image distance, the image height, and the attributes using the thin lens equation. This is going to be HO, 2.5 centimeters. By the way, I can use centimeters here, right, because the units end up canceling. HO is 2.5. I'm going to say DO is 10. And I'm going to say F is what, 5.0? Is that right? Negative 5.0, because it's a diverging lens. Therefore, the rays don't really go through the focal point. They virtually go through the focal point. They diverge away from the focal point. We want to determine the image distance, DI. We want to determine the image height, HI. We want to determine the attributes of the characteristics, which we'll worry about once we have our numbers. Usually our numbers tell us what the attributes are. We won't draw a ray diagram because we've already drawn all of the possible ray diagrams. So here's what I want to do first. 1 over F equals 1 over DO plus 1 over DI. We're going to say 1 over, don't forget the negative, 1 over negative 5 equals 1 over 10 plus 1 over DI. I almost always rearrange equations before subbing numbers in here. This is one exception. Don't rearrange this first. Do not rearrange this first. Sub your numbers in with the signs and then rearrange it. Now, I showed you a little trick on the calculator on Thursday, to rearrange this. Some of you are good at fractions, some of you are terrible at fractions. Okay, you just have to be good with your calculator here in order of operations. 1 over negative 5. So I say negative 5, x to the minus 1. 1 over negative 5. Subtract 1 over 10, or 10 x to the minus 1. Right, I want to take the 1 over 10 over by subtracting, so I can get DI by itself. But when I do that, I get negative 0.3. That doesn't equal DI, that equals 1 over DI. Well, so what I got to do with that is flip it over. Take the inverse of it. So just x to the minus 1 of my answer there, and I end up getting DI as negative 3.33. Now, that's enough right now. Like, I just calculated image distance, but the negative in front of that is enough to tell me something about the image. What do I know about the image besides where it is based on that number? What is it? Well, okay, it's not actually inverted, but that is, it is enough to tell me whether it's upright or inverted. It is upright. Okay, but that's not what I was thinking. Okay, I look at that negative, Nathan, think it's a virtual image because it's a negative DI. A negative HI would tell me that it's inverted, right? But now, if you remember the patterns, you remember that a virtual image is always upright, right? A virtual image is always right side up. So you can determine that characteristic as well. Although, you're going to see in a minute, there's another way to determine whether it's right side up or inverted. Bottom line is we now know that this is a virtual image because it's a negative DI. Now let's get HI. let's say HI over HO equals negative DI over DO. That's two parts to my magnification equation. HI is what we're looking for. HO is 2.5 equals negative 3.33, because it's negative DI, negative of negative 3.33. DO is 10. Let's figure this one out. Let's say negative 3.33 divided by 10 times it by 2.5 gives me 0.83. Okay, what does that tell us? The fact that it's positive tells us that it's upright, which, if you remember the patterns, you already recognize that it was upright, because a virtual image will always be upright. But there's a nice little check in that for us, right? The number tells us that it's what? Yeah? Smaller. The object was 2.5 high. The image is 0.8 high. The image is smaller. So whenever you see these questions where you're looking for the attributes of the characteristics, they're important. But just solve for things. Solve for things, even if they didn't ask me for these numbers, get them anyways. And that's going to tell you the attributes. Now, having said that, if they didn't ask you for the numbers, you'd have a choice. You could calculate those numbers and get the attributes from the numbers like we did. Or, if they're just asking for the attributes, you could draw the ray diagram and get the attributes that way, whatever works better for you in that case. All right? Questions here? Let's take a look then at 3 questions on page 681. Okay, let's have a look at question number 2. It says a 10 centimeter high candle is placed 100 centimeters from a diverging lens. First thing we want to do is circle that to draw our attention to the fact that it's a diverging lens. Remember that a diverging lens has a negative focal length. Okay, if we forget that, then we're kind of hooped on this. Determine the following using a ray diagram and the thin lens equation. We're not going to worry about a ray diagram. We've done the ray diagrams, all 10 possibilities. So let's just use the thin lens equation. We want to find where the image is located, so in other words, DI, the image height, HI, and the type of image formed, so whether it's real or virtual here. What do we got? 10.0 centimeters, what is that? That first number, number 2. Is that DO, HO, M, DI? What is it? What do you got there? Thomas?
The first number they give us?
Yeah.
Yeah, that's HO.
Good, that's the object height. Now it doesn't actually say whether that object is right side up or upside down, right? If it doesn't say, then assume the object is right side up. 99 times out of 100, the object will be right side up. What else we got? 100 centimeters. By the way, we can use centimeters, right, as long as we're consistent and use centimeters throughout the question, because the units end up canceling. What is that? What does that 100 centimeters, Nathan, represent? Good, DO, the object distance. And we've got a focal length, F, of 25 centimeters, right? Is that right? Focal length of 25. Somebody said no. What is it? Should be negative 25. Good, because it's a diverging lens. I don't forget that because I wrote a note about that. We want to determine the image location, DI. We want to determine the image height, HI. And then we'll worry about C later on once I calculate those numbers. Probably going to start with the lens equation. If you start with the other equation, that's okay. There's only 2 of them. So if one doesn't get you the answer, then try the other one. I know what F is, so I'm going to plug in negative 25. DO is 100. And I'm looking for DI here. So how am I going to do that? Well, remember, on the calculator, there's the little trick here. We're going to say, we've got to say 1 over negative 25. And then we've got to subtract from that 1 over 100. The easiest way to do that is on your calculator to say negative 25 x to the minus 1. That's 1 over 25. Subtract 100 x to the minus 1. Okay, that's negative 100. Gives me negative 0.05. But that's not DI. That's still 1 over DI. To solve for di, I've got to swap places and ended up taking the reciprocal of negative 0.05. So let's flip that over. 0.05 x to the minus 1 gives me negative 20. So there's di, negative 20. That should actually be 3 digits, right? Negative 20.0 centimeters. Right away, we know where the image is, so A is done. We also know C, the type of image formed. What kind of image do we have formed here? What kind of image is formed here? Yeah. It's virtual, and how do you know that?
It's a diverging lens.
Okay, interesting, actually. I didn't think of that, actually, when I read the question. A diverging lens, if you remember your patterns, a diverging lens always produces a virtual image, right? So we didn't have to do any calculations to determine that was going to be virtual. Okay, I didn't catch that. Okay, Thomas did, I didn't catch that. Okay, I looked at this number and determined that it was a virtual image because this number is a negative di tells me that the image is virtual. Make sense? Now, you weren't asked in this question whether it's right side up or upside down, but if you remember the patterns of my ray diagrams, then you're going to remember that a virtual image is always which way? Right side up or upside down? Upright. Yeah, it's always upright. Okay, let's determine the image height now. Let's say HI over HO equals negative DI over DO. Let's say HI is, that's what we're trying to find, isn't it? HI is what we're trying to find. HO is 10.0. Negative DI, once again, negative 20 over DO is 100. I think when we do the math there, it's going to work out to be 2, isn't it? Let's just check it here. Negative 20. Let's say negative 20 divided by 100. And now let's times it by 10. Gives me 2. Didn't we say it was also upright? We weren't asked for that, but we also said it was upright because virtual images are always upright. Positive HI is confirmation of that, right? Like, you don't have to remember those patterns, but if you do, man, it sure is nice sometimes to have confirmation that you've done something right. Okay? I determined that it was going to be an upright image earlier on when I said, oh, it's going to be the same. It's going to be upright because it's virtual, and virtual is always upright. And then I just calculated HI, I got a positive value. Oh, it's upright. Okay, if I happen to get a negative value for HI, then I did something wrong somewhere, right? Because that would be contradicting what I determined earlier about the orientation of it. Okay, have a look at worksheet number 18 now. For now, at least, just questions 1 to 3.